Good morning, folks. So I'm all ready to do a demonstration for you. And then we're going to get into a little bit of chapter 13 today. And whatever we get through today will be what's on the exam next week. So we'll talk a little bit about that at the end of class. So hopefully we'll have a little bit of time to do a little bit of review if we need to. And then I'll talk to you about a review session. So this is the slide we ended on last class period. And I told you this was pretty much all I was going to talk to you about in terms of sugars, right? And I told you that we have dextrose here, right? And so this is, what's another name for a sugar? Well, starch is a sugar, yeah, but there's another name that I'm thinking of. Yeah, carbohydrate, right? So if you look at the molecular formula of this sugar, you will find that it is perfectly just pure carbon and water when you look at the molecular formula, okay? How many stereocenters does dextrose have in this form? How many chiral carbons does it have? Is this a chiral carbon? Yep, so there's one. How about this one? 2, 3, 4, 5. There are 5 stereocenters that are all lined up together. So if nature made this at random, what would be the maximum number of dextrose molecules that could exist? What's the formula? 2 to the 5th, which is what? What's 2 times 2 times 2 times 2 times 2? 32. I believe it's 32, yeah. If nature made this sugar at random, there would be 32 unique, a maximum of 32 unique molecules for dextrose. Mother Nature makes 1. Mother Nature makes 1. This carbon that I'm pointing to here, I'm pointing to it for a very particular reason. That's called the anomeric carbon. A-N-O-M-E-R-I-C, anomeric carbon. You're going to learn about that if you haven't already learned a little bit about it. You're going to learn about that in biochemistry when you all talk about carbohydrates. Okay? It's the carbon that you have to pay attention to know whether or not your sugar is a reducing sugar or not. And this anomeric carbon right here is this carbon. It's the carbon of the aldehyde if this was ring opened. Okay, so remember I told you that you can place these simple sugars in water and they're in equilibrium with the aldehyde form, right? So this is the aldehyde carbon right there, and we call that the anomeric carbon. How many stereocenters are there in the ring opened form? Hint, just count the solids and dashed wedges. How many do I have? 4, right? So there are 4 stereocenters in the open form. There are 5 stereocenters in the ring closed form. And that's because when this alcohol comes around and forms a hemiacetal, which is what we talked about last time, it forms a new stereocenter here. Okay, so you get an extra stereocenter. That means that these sugars can exist in what are called the alpha and beta anomeric forms. You all will talk an awful lot about that when you get into biochem. But the important thing about the difference is that like the alpha anomer can link together to make starch, the beta anomer can link together to make cellulose. It's the same sugar, just a different structure of the one carbon. And that means that you have very different properties. Starch is soluble in water, cellulose is not. It's a good thing, right? Cotton is cellulose. You don't have any problem washing your clothes. You won't wash your clothes if they were made of starch. Well, you would try and they would dissolve, right? Wouldn't be very good. So, what we're going to do today is we are going to do the Tollens test on this sugar. I'm going to prove to you that it's a reducing sugar. And what the Tollens reagent does, remember, is it will take an aldehyde and it will oxidize it to a carboxylic acid ultimately. So aldehydes can be oxidized to carboxylic acids using the Tollens reagent. And the cute thing about this is that the oxidation occurs on the carbon, but the silver gets reduced. So the silver that's positively charged in solution gets reduced to silver metal. And we talked a little bit about that last time, right? And we talked a little bit about the properties of silver, right? My ring is silver, right? It looks like a mirror when I'm looking in it, right? We're going to make a mirrored flask here. And so I've got to make the Tollens reagent. The Tollens reagent is silver ammonia complex. And so what we do is we take a little bit of silver solution. And I'm going to use, you see the brownish color on the, that's because this has always been used for silver solutions. Silver's photoactive, and so it precipitates out over time. That's why I've got the silver solution with a bottle that's taped up to keep as much of the light out as I can. And I'm going to silver this flask. Right, this is a 125 milliliter Erlenmeyer flask. Can you tell me anything about the flask just looking at it? It's clear. It's very clear, in fact. My graduate student did a special cleaning for it. We actually clean these if we're going to do this reaction with concentrated nitric acid. So it completely cleans the inside of it. Really nice. So that is about as clean as you can get. So I'm going to start off with about, let's see, what's the recipe called for? About 30 milliliters of this silver nitrate solution. So we'll pour in some silver nitrate. Get about 30 milliliters of it. Close this up. Pour it in the flask. Anything special? Nothing special yet, right? And now we're going to add some ammonia to it. When you all buy this stuff, it's called ammonium hydroxide is the name of it. But ammonium hydroxide is not really a true statement. You can't actually have ammonium hydroxide. I'll leave that for you all to think about. It's really nothing more than ammonia and water. And you all might smell a little ammonia. Because I can. Tell me what happens when we start adding it. Kind of turns brown, right? See what happens as I continue to add. It goes back into solution. Isn't that neat? Keep that. Woo! Now, what I've just made is I've made the silver ammonia complex, what you're seeing here. Okay? I know that I made it because it all went back into solution. I know that the silver ammonia complex is perfectly soluble in water. Okay, so I know I've got that. What else do I need to add to make the Tollens reagent? What else is up there that I haven't added yet, other than the sugar? I haven't added hydroxide yet, so I've got a little thing here of about 0.8 molar potassium hydroxide, and I need to add about 15 milliliters of that. So I'm going to just guesstimate here, pretty close. That's about 15 milliliters. Potassium hydroxide. Let's see what happens now. Solution. Not a whole lot happened there, did it? Right, so that's pretty good. Should stay in solution. I'm going to add just a little more ammonia for good measure here. Sometimes it precipitates out. You got to add a little more ammonia. So when it doesn't do that, I add just a little bit more for good measure. Okay. So now I've got my Tollens reagent. Now what do I got to add? What do I need to add now? Need to add the sugar, don't I? There's my sugar solution. It's dextrose. It's that molecule up there. It's just in water. And I'm going to add, it doesn't really matter how much we add, but I'm going to add about 5, 6 milliliters, something like that. Got to add enough. Starting to do something, isn't it? Starting to change color on me. I gotta get it stoppered here pretty quick. Now, just gonna go to shake. So you can clearly tell that that solution is no longer clear and colorless, is it? I can still kind of see through the flask though, can't I? Let's see what happens as I keep shaking. Y'all starting to see anything happen on the flask? Anything happening? What's happening? It's becoming more and more reflective, isn't it? Yeah, that's the silver plating out on the flask, and I'm gonna just keep stirring it till I get a nice silver mirror. This is how, when you go to the mountains, like I told you last time, and you buy one of those fancy homemade or handmade Christmas ornaments that's silver, this is how the guy does it. Or the lady. This is how it's done. They blow the glass to whatever shape they want, and then they make the Collins reagent, put it in there, and they start shaking it around. Now it's really starting to look like a mirror, isn't it? I can start to see my mug in it. All right. Make sure we get a nice silver mirror. So what did I promise everybody? One for every A. That's right. On exam 3, everybody who makes an A gets a flask. And I hope it's not just this one flask that I have to make. Okay? So, I want you all to make it hard for me to where I have to be up here all weekend making flasks. But I think you all will agree that looks like a mirror now, doesn't it? So I'm going to probably call that good. Make sure it's good. There we go. Make sure I don't get any of this on my clothes or my wife will kill me. And I think I just did. In fact, I know I just did.
Lab safety, 8 out of 10.
That's right, yeah. I didn't pass that test, did I? All right, so now what I'm gonna do, is I'm gonna rinse this out very carefully, so I don't scratch any of the stuffs. And I forgot to bring paper towels, so I'm gonna run to the men's room real quick. I'll be right back. Ooh and ah over that. I'll be right back. Got my graduate student coming to pick up the stuff. And one of the things that I don't tell you is that Tollens reagent, that stuff that's sitting in there right now is absorbing nitrogen from the air, and it's making what's called silver nitride, which is explosive. So, we kind of need to get it out of here. Good news is, as long as it stays wet, it won't blow up. Okay, you're all safe. And even if it did, the amount we've got wouldn't be like a firecracker, not anything else. No, nowhere near TNT, no, not at all. Not bad if I do say so myself. So I'm going to pass that around. Y'all can take a look at it. You can take a photo of it. You can do whatever you want. Just don't stick anything in it. It's a very thin layer of silver, and you can scratch it, and then I've got to redo it. And I'm really not wanting to do that. So would appreciate it not doing that for me. Put away my materials here. So what was the organic product that we just made? What happened to the sugar? It became what? It did. Yeah, that's exactly right. Technically, it's a carboxylate because it's in base. But yeah, that's exactly what happened. Thank you, Thomas. Yep. Appreciate you. Anybody need a single glove? Apparently, I grabbed 3. So that is the flask. It's about a dime's worth of silver, about a $6 flask. The flask is actually more valuable than the silver. It's there, but it's kind of cool looking, right? Kind of fun. Okay, and so that's what's happening in this. So we know we have a reducing sugar because, and then in the old days, this is how biochemists determined whether or not they had reducing sugars or not. They would use this test, or there's another test that they would use that uses copper. It makes a copper mirror, and copper's cheaper than silver, so they would frequently use that. But it's the same kind of test to make the silvered flask. Okay, and then you all turned in a quiz, which I've graded and posted, but I forgot to bring with me, so I apologize for that. I'll bring it next time. So before we jump into this stuff today, let's go back over the stuff from last time real quick. So let's do a little review. So if I take an aldehyde or a ketone and I react it with water, what do I make? I make a hydrate, right? If I take an aldehyde or a ketone and I react it with an alcohol, what do I get? Acetyl, an acetal, yeah, we get an acetal functional group. If I take a aldehyde or ketone and I react it with a primary amine, what do I get? An imine, an I-M-I-N-E, yeah, an imine, right? So if I take let's just pick on an aldehyde. So if I take an aldehyde, water, and a little bit of catalytic acid, I get a hydrate, right? If I take that aldehyde and I react it with a primary amine, I get an imine, right? That was the chemistry that's important for your eyesight, right? You've got basically a photon antenna, right, that's attached to a protein through this type of bond, and it's reversible. Remember, all of these things are reversible, so we can go back if we need to, right? And then if I take an aldehyde and I react it with an alcohol, at least two equivalents of that alcohol, I make an acetal. Right? So those are the types of things that we learned last time that we could do with aldehydes and ketones. I can also take an aldehyde, right, and I can react it with, what kind of reagent is that? Grignard. If I take an aldehyde and a Grignard, what do I get? I get a secondary alcohol. After workup, of course. Right, so there's a lot of things I can do. I can take a Grignard, react it with an aldehyde, I get a secondary alcohol. I can take a Grignard, I can react it with a ketone, and I get a tertiary alcohol. I can take a Grignard, I can react it with formaldehyde, and I get a primary alcohol. Right? These things are going to have to roll off for you on the next exam. Okay? You're going to need to know that these things get made. We didn't focus an awful lot on the mechanisms, and that's okay. Right? We're not going to focus too much on that. All right. Chapter 13, the stuff that we need to talk about for today, is all about carboxylic acids. Right? We just kind of talked about carboxylic acids. Tell me how to draw a carboxylic acid. How would I draw that functional group? Who's got my flask? Done with it? Pass it back. Have you all had a chance to see it? You already saw it? Okay. I don't want anybody walking off with your award and things. That's one of my better ones, actually. If I do say so myself. So tell me how to draw a carboxylic acid.
Acetyl onto an O onto a
What else do I need?
attached to another marker.
Yeah, attached to something else, right? Yeah, so anything else. So this is the carboxylic acid functional group, right? Where would I find diagnostic signals for the carboxylic acid in the IR spectrum?
You would find it further to the left.
What would I find further to the left?
The OH.
Okay, yeah, the OH will be in that hydrogen region, that's certainly true. So this will be somewhere around 3,300 and it'll be kind of broad, kind of look kind of like that. It won't be nice and symmetrical like an alcohol. What else would I need to see?
SP2 region.
The SP2 region, so somewhere between 1,500 and 2,000, I would also see a peak for the carbonyl, right? So that's definitely going to be diagnostic of a carboxylic acid, right? And so that is the functional group. What do we know about the chemistry of this functional group? Can you tell me about carboxylic acids?
It's an acid.
It's an acid, yeah. It's acidic. Are they strong acids or weak acids?
Strong acids.
For inorganic chemistry, they are strong. Would you consider them strong though if you were in Gen Chem? No. These have a pKa somewhere around 4 to 5, right? So they have a pKa kind of in that region, approximately 4 to 5. Strong acids that you learned about in Gen Chem, though, have pKa's that are below 0, right? They completely dissociate when you place them in water. These do not completely dissociate when we place them in water, okay? They will dissociate, but they don't completely dissociate. Okay, so overall, these are weak acids, but to an organic chemist, these are actually quite strong. Okay, so it's one of the stronger acids that you have in organic chemistry is the carboxylic acid function. Okay. Tell me some carboxylic acids that you know about. Anybody like Italian dressing? Or oil and vinegar? Right? What acid are we talking about? It's acetic acid, yeah. Comes from, there's apple cider vinegar, there's, but the fermentation of fruits quite frequently gives you alcohol. That alcohol then gets further oxidized to carboxylic acids. And that's what is the acidic component in vinegar. You all are probably familiar with several different types of vinegar: balsamic vinegar, white vinegar, distilled vinegar, apple cider vinegar, yada, yada, yada. Just depends on what the starting food stock was that was used to make it. But in all of them, the acidic component is that carboxylic acid functional group, okay? So you will find us drawing these out several different ways. Of course, kind of the general formula that I just drew there with the lone pairs of electrons. You will find sometimes in books where they will just draw it out as COOH or as CO2H. All of those by sight, you need to look at it and say, that is a carboxylic acid, okay? That is a carboxylic acid. Okay. Naming for carboxylic acids, I'm not going to focus too terribly much on the naming. You all can kind of get this on your own, but there are a few that are kind of important. So usually you find the parent alkane like you would, and then you drop the A and E ending in that OIC acid. So acetic acid, the parent is 1, 2, because there's a CH3 here. That's ethane, right? This is also known as ethanoic acid. Nobody calls it ethanoic acid, they call it acetic acid, okay? It's just historical, okay? The one that you see here, tell me something about that name that's the systematic name, not the one in parentheses. 3-methylbutanoic acid. What's weird about that name? Yeah, the 3. Why is that weird? So if you went from left to right, it would be 2-methyl, right? And what was the rule we learned in naming alkanes? Lower better, right? So why is this 3-methylbutanoic acid?
There's a special rule.
There's a special rule. What's that rule? What can you discern that rule to be from looking at this? You start at the carboxylic acid. The carboxylic acid carbon is carbon number 1 when naming carboxylic acids, right? The longest chain, right, is 1, 2, 3, 4. So that's where we get the butane part. Since the functional group is a carboxylic acid, it's going to be butanoic acid. And then it's 1, 2, 3, 3 is where the methyl is. This is also known as isovaleric acid. This stuff stinks bad. It smells. It really smells. It's a stink bomb kind of smell. The molecule that we have here, this is trans-3-phenyl propanoic acid. Dissect that name for me. Dissect that name for me. What does that mean? Can. C6H5 is what kind of ring? What kind of ring is that? That's a benzene ring, right? So that's an aromatic ring, right? So that's an arrow group or a benzene ring. It's attached to the rest of the molecule. Why is it 3? Why is it 3-phenyl? Again, the carboxylic acid takes priority. 1, 2, 3. Right? So the phenyl group is on carbon number 3 of propanoic acid. What does propanoic acid tell me?
Propanol, but it has a double bond.
Yeah, it's an alkene, right? It's got that. So notice that they're putting the ene in there. So this has the formula of a propene, but it's a carboxylic acid. So it's 3-phenyl propanoic acid. And then why do they say trans? It's the trans isomer about the double bond. What does trans mean?
Different side.
Right, so the aromatic ring and the carboxylic acid are on opposite sides of this plane. Right, they are trans to one another. Can we have cis? Yes, we could imagine cis, and there is so-called cis-cinnamic acid. But cinnamic acid is trans-3-phenyl propanoic acid. Cinnamic acid, where do you think that stuff is found in? Cinnamon, yeah. It is a cinnamon-derived organic molecule. Yep. Okay, so here's a few more examples. 5-hydroxyhexanoic acid. It's a common carboxylic acid that I think you find this one in cosmetics. 5-hydroxy. And again, you've got 1, 2, 3, 4, 5. How many stereocenters does 5-hydroxyhexanoic acid have?
Two.
Show me where.
The carbon attached to the OH and the carbon attached to the OH.
Okay, so this one? So that would be this carbon, right?
Oh, so it's double bonds.
Yeah, so it can't be, right? So again, remember, drawing it out like this is the same thing as this. Okay, so don't confuse this as being two different oxygens singly bond, or two different oxygens singly bonded to that carbon. That's not the way it is. Remember, one of those has to be doubly bound, okay? Here's 4-aminobutanoic acid. What's kind of weird about this acid? What did we learn about amines? What do we know about amines? What kind of amine is that?
Primary.
That's a primary amine. So we've got a primary amine and we've got a carboxylic acid. Why should that be making you go,
Lone pair.
There's a lone pair on the nitrogen, right? That's true. What else? Are amines acids or bases? They are bases. I've got a molecule that has a base, a very good base, and a pretty strong acid in it. What do we know that acids and bases like to do with each other? They like to react and neutralize each other, right? We're going to learn more about this in the next chapter when we talk about amino acids. This is an amino acid, okay? It's a simple amino acid. It's not one that's terribly common in making proteins or anything, but nonetheless, it has these two functional groups that are kind of at opposite ends of the spectrum, if you will. And so that really creates an interesting situation because you can, under certain conditions, you can make the molecule act like an acid, and under certain conditions, you can make it act like a base. And that's kind of cool, right? You can start to do a lot of things with that kind of thing. What kind of functional groups are in this 5-oxohexanoic acid other than the carboxylic acid? What's the other functional group? Question? What's the other functional group?
Ketone.
It is a ketone, right? We've got a ketone at the 1, 2, 3, 4, 5. Notice in the naming, they name a ketone through this, they call it oxo. I'm not going to examine you on that, okay? But this is 5-oxohexanoic acid, and we know that it has to have a ketone at the 5 position, okay? We can also have molecules that have multiple carboxylic acids in them. These are just a few examples. These are called dioic acids. And so since there's two of them, you'll notice in the name, it's dioic. Ethane dioic acid. Where does the ethane come from? Do you see ethane there anywhere? It has 2 carbons though, right? The longest chain is 2 carbons long. And those 2 carbons happen to have carboxylic acid, so it's ethane dioic acid. Okay? This is also known as oxalic acid. It's a biological acid, it gets produced, right? I believe, I might be wrong, but I believe this is one of those acids that you feel when you work out really hard and your muscles start to burn. I think that is oxalic acid, okay? Here's another one. This one is my favorite dioic acid. We use this all the time in my laboratory for the chemistry that we do. This is propane dioic acid. It's also known as malonic acid, okay? It's cheap, readily available. It actually costs more to have them ship it to me than to buy it outright. So we have lots of this in my lab, and we use it to make all sorts of things. Okay. One of the things that an organic chemist is always interested in, it's not just can you make the molecule, but can you make it without breaking the bank? Right? I can make all kinds of things very, very expensively. But to make them cheaply enough that people can actually afford to buy them as medicines or materials that they put in their car, that's the trick. Right? You can make just about any molecule you want these days. The trick is to make it economically viable, right? You all don't want to go to the pharmacist and have to pay $10,000 a dose for your medicine, right? It's already more expensive enough, right? And so chemists are always trying to figure out how do we take what's cheap, readily available, and convert it into something that we want. Succinic acid, that's butane dioic acid. It just has one more carbon between here compared to malonic acid, so that's called succinic acid. And then you have glutaric acid, and then you have hexane dioic acid. This is called adipic acid. Polymer friends will probably know a little bit about adipic acid. There are a lot of adipic acid derivatives that are used in a variety of polymers, so that are commercially available. So all of these things are called so-called dioic acids, and they all have industrial uses, if you will. They're very cheap, readily easy to afford. If you have the carboxylic acid bound to a ring, you're going to number the ring such that you give the lowest priority to all other functional groups. Again, the carboxylic acid is going to take that number, it's going to take priority, right? So this is going to be number one of the ring, and then you're going to number in a counterclockwise fashion here to give the alkene the lowest possible name. Okay, so this is 2-cyclohexene carboxylic acid. Notice the 2 tells me what? It tells me where the alkene is. It doesn't tell me where the carboxylic acid is because I know that has to be number 1. Here's another example of a dioic acid, right? This is trans 1,3-cyclopentane dicarboxylic acid or dioic acid. Okay? Is this molecule chiral? Does it have stereocenters? If I'm asking the question, what does that probably mean? Probably it does, right? Where are they? Is that a chiral carbon? Nope. Is that one? Certainly is. Is that one? Nope. Nope. Yep. So we've got 2 chiral centers. 2 squared is 4. There's 4 possible maximum number stereoisomers, right? There are 4 possible. But there's actually fewer than that because if I make this stereoisomer, is that molecule chiral? This is a stereocenter. This is a stereocenter. But this will not rotate plane polarized light. This is not a chiral molecule. It has a mirror plane. Remember, we cannot have mirror planes in chiral molecules, right? So, actually there are only 3 possible stereoisomers for this molecule instead of 4. Remember that equation is the maximum number, not the actual number. Okay. Talk a little bit about some aromatic carboxylic acids that are common. This is benzoic acid. You can see why the name is what it is. Benz from benzene. We don't call it phenolic acid, we call it benzoic acid. It's a benzene ring attached to a carboxylic acid, okay? You all are very familiar with this molecule in its salt form. Okay, so they take this molecule and they react it with sodium hydroxide and they make the carboxylate salt, which is very soluble in water. Where might you all encounter this? How many people in here like to eat Chinese food? Just about all of you. You know, the Kikkoman sauce and all that, it is preserved with sodium benzoate. Okay, so you're actually eating a preservative that is made from benzoic acid, okay? And we've learned that a benzene ring is carcinogenic. Right? Pure benzene is highly carcinogenic, but you put a substituent on it and all of a sudden it becomes a food preservative. Kind of amazing, making just a little change can make a big difference, right? The only difference between benzene and benzoic acid is carbon dioxide. It's just CO2. So add some CO2 to benzoic acid and now or to benzene and you've got a food preservative. 2-hydroxybenzoic acid. This is known as salicylic acid. What do you all know about salicylic acid? Pardon? It's used in acne products? Okay, what else do we know about it?
Can be used to make aspirin.
Huh?
Can be used to make aspirin.
It is used to make aspirin. Did you all make aspirin this semester? Yeah. So you all took salicylic acid and probably acetic anhydride and made acetyl salicylic acid. It turns out that the salicylic acid is what is responsible for the curing your headache, so to speak. But it's really rough on your stomach. You will get an ulcer if you take too much aspirin, actually. And so what they do is they acetylate the hydroxyl group, and it makes it more tolerable to your gut. Okay, kind of a prodrug, as we call it. Right? You kind of mask the drug, and then it gets formed in your body through hydrolysis. Okay. Anybody know what else salicylic acid? So we've got it's used in acne medicine. It's used in aspirin. What else? It's actually also used in wart remover, those patches, that creamy stuff, if you use that. Salicylic acid on those types of growths, it will dissolve them over time and help remove that. They also use it a lot on cattle. So if they mess with a cow's hoof and they got a growth on it, they will add salicylic acid, they'll wrap it up, and that will remove that growth over time. So there's a lot of things that salicylic acid is used for. Phthalic acid and terephthalic acid. You probably don't come into contact with these in any type of foodstuffs, but you do come into contact with them. So terephthalic acid especially is manufactured on a huge scale, and it's used in the plastics industry an awful lot. So terephthalates are used as plasticizers. It's what gives the plastic its plasticity, and I know I'm using a word to define itself almost, but you can learn more about that by walking across the street to the polymer department. But these types of molecules are used an awful lot in the polymers industry. The materials that you all use and take advantage of rely on these types of molecules. There's actually a company in Tennessee that all they do is make this molecule on a huge scale. And I interviewed with them back 20 years ago when I didn't know whether I wanted to go into teaching or industry. And it seemed pretty boring to me. They just worked trying to figure out better ways to make the same thing over and over again. But they paid well, so, but I ended up here. So, when we're talking about carboxylic acids, you'll quite frequently find that we use the Greek alphabet. So, of course, carbon number 1 is going to be your carboxylic acid carbon. And that means that then the one attached to it would be 2, 3, 4, 5, and so on. But in reality, people think of this not so much as carbon 1, but as a functional group, right? And so when you think about this as a functional group, you would say this is carbon number 1 removed from the functional group, carbon 2, carbon 3, carbon 4. And so to get around that conundrum, we actually call this the alpha carbon. The alpha carbon is the carbon directly attached to the carboxylic acid functional group. You can have the beta carbon, the gamma carbon, and the delta carbon. And beyond that, I start to forget my Greek alphabet. Those of you in sororities and fraternities probably know it better than I do. But here's a molecule called GABA. It stands for gamma aminobutyric acid. It's a simple amino acid. So alpha, beta, gamma, right? So there's the gamma carbon that contains the amine. This is actually a simple amino acid that is used in your brain. Okay, and there are a lot of studies on making GABA analogs to help control mood and other types of mental situations. So GABA is something that is studied in biology quite a bit and easy to make. All right, we'll skip that one. All right, so I want you all to think about this problem. I want you all to get in groups. You all have heard about omega fatty acids in nutrition. So this is talking about omega fatty acids, and there's the problem. All right, so read that problem, look at the structure, and then try to answer that question. How many cis and trans isomers are possible for this particular polyunsaturated fatty acid? Get together, work through it, take a few minutes.
So does omega always mean end carbon? Or is that a number?
It means towards the end, yes, so omega is always at the end. It's the end of the Greek alphabet, right? The alpha and the omega. It's kind of a biblical saying. What are you thinking?
64.
64. 64 what? Cis-trans isomers. Okay. How are you coming up with that number?
Well, cis-trans is only two options, so there's six alkane or carbon-carbon single bonds, which would be able to allow that. So 2 to the 6th power would be 64.
Okay. Okay. So you're basically saying each one of these alkenes, right, could either be in the cis or trans conformation,
Alkanes, but yeah,
or alkenes.
alkenes.
Yeah, right, C double bond C, right?
I was saying single bond.
Yeah, the single bonds are all gonna be here, right? Everything else is gonna be doubly bonded in here, right? Except for this, right? So I've got, you're right though, I've got a possibility of being cis or trans in each one of these. So I can have one of them being cis and all the others being trans. I can then have two. Yeah, so it's gonna be a pretty good sized number, isn't it? But each and every one of those bonds can either be cis or trans. That's right. So you've got 5 of them, right? You got 2 options, so that would be 2 to the 5th. Is 2 to the 5th 64? What is 2 to the 5th?
32.
32? Yeah, so you doubled it somehow. I don't know how you got to the doubling. But you can have 2 choices, either cis or trans in each one of those. And you're right, that they all can be cis or trans, and so figuring out what the maximum number would be, it's actually pretty big, right? It's not just 5. You have 5 things that can be cis or trans, but when you start talking about combinations, it's just like talking about combinations of a regular stereo center, right? And so that's how one has to think about that. All right. Let's talk a little bit about some of the physical properties of carboxylic acids. And it turns out that pure carboxylic acid, so if you take pure acetic acid, that is, you take vinegar and you remove every bit of water and all you're left with is the acetic acid, it will start to form what's called a hydrogen bonding dimer. Okay, and so the carboxylic acids start to form these rings. How many atoms are involved in these rings? There's 8, yeah. You form this dimer, it's kind of an 8-membered ring, right? And the acidic hydrogen of one carboxylic acid will interact with the carbonyl oxygen, and the acidic group of the, or hydrogen of the other one will interact with the other's carbonyl, and these form these dimers. So what do you think that's going to do in terms of the boiling point or the melting point of these things? Is it going to impact it? Yeah, definitely, right? And what you find is that these molecules actually have very high boiling points because of this dimer formation. So carboxylic acids typically have higher boiling points than most organic molecules because they form these hydrogen bond dimers. And a hydrogen bond is a strong interaction, right? And so you form these dimeric structures. Now, when you dissolve them in water, the water disrupts that. Okay, and you start to get hydrogen bonding with the water, and that's what makes the carboxylic acids soluble in water. Okay, so again, you're going to find much higher boiling points. I mean, carboxylic acids quite frequently have boiling points much higher than 100 degrees. There are a few examples where they have low boiling points, but for the most part, they're quite high. Okay, and they form these strong intermolecular hydrogen bonds. They form. They're very soluble typically. They do follow the 5-carbon rule. So for every carboxylic acid, if you have 5 or fewer carbons, chances are it's going to be soluble in water, right? What do you think is going to happen between the carboxylic acid and the salt of the carboxylic acid? Is making the salt going to increase the solubility or decrease the solubility? What do you think? Are salts more soluble or less soluble in water typically? Pardon? They're typically more soluble. Depends on what the salt is, of course, right? But typically salts are more soluble in water than things that aren't salts, right? And so we can play with that. a little bit, okay? And in fact, we do mess with this an awful lot, okay? This is a simple carboxylic acid. It's called decanoic acid. So decanoic, how many carbons are in the longest chain? 10. So this is a 10 carbon carboxylic acid, right? So we got carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's decanoic acid. You all probably, at least within the last week, have come into contact with something like this, maybe not this particular molecule, but these things make soaps. Soaps, what does a soap do? Used for cleaning, yeah. How do they work? How does a soap work? Okay, they do. Some of them make bubbles, but the bubbles really don't have any cleaning action. Right? The scrubbing bubbles nonsense that you see on TV, that's just to make you think it's clean. Right? I can actually show you some soaps that don't make much bubbles and they clean really, really well. What is it about soap that makes it clean so well? Why is it that you put soap in with your clothes?
Dissolves oils.
Okay, we're trying to get like body oils and other dirt and grime that normally doesn't dissolve in water to dissolve in water. I think that's what you both were trying to get at, right?
It has a polar and non-polar end.
Has a polar and a non-polar end, or a water-loving and a water-hating end, right? Hydrophilic and hydrophobic portions, right? We're going to talk a little bit about that here in just a second. But this will kind of blow some of your mind if you've never heard it. Soap makes water wetter. Wetness is the ability to clean something, right? That's what soap does. It makes water wetter. It makes it remove the dirt and grime a lot easier, okay? And so we have this piece of the molecule, this carboxylic acid, and we know that carboxylic acids like to form hydrogen bonds with water. What do we know about grease? Does it like to interact with water? What happens when you go home and you try to make your vinegar and oil salad dressing? What happens when you mix the two together? Do they mix? No, they form two layers, right? You have to shake it up and then pour it out real quick so you have the right ratio, right? So here we have a molecule that has a piece of it that likes water, and we have a piece of it that hates water. What do you think is going to happen if I take a bucket of this and throw it into a pool of water?
Only some of it will react to water.
Okay, some of it. What does that mean?
The part that likes the water.
The part that likes the water is going to interact with the water. Okay, what's going to happen to the other part? Is it going to just stick its tail up outside the water and, no, what's going to happen?
It's gonna float in the water.
Potentially could, but when we dissolve soap in water, do we see the soap float on the top? We don't see that, do we?
Usually not that squeeze.
Think about it. How could I make this to where it will completely dissolve in water? I've got half of it, or a portion of it that we call the tail. We've got this long tail that hates water, and I've got this little tiny head area, this head group as we call it, that loves water. How can I arrange those in 3 dimensions such that it dissolves completely in water? How can I take those molecules and put them side by side to dissolve them in water? To make it dissolve in water? How could we do that? Think about everyday shapes that you might come into contact with, especially if you like sports. What kind of shape could I put these molecules into that would make it completely love water and dissolve like a soap? Ah, a sphere, yes, like a baseball or a softball or whatever your favorite ball is, right? So I can imagine a 3-dimensional sphere. My pen's running out here. So I can imagine a 3-dimensional sphere. I'm just going to look at a slice of it, okay? And so out here is water. Here's my head group that loves water. Here's my tail, right? There's my head group, there's my tail. So all of the tails are on the inside hating water. Like dissolves like, right? And on the outside of that sphere is all the polar head groups that love water. This is how soap works. This is what happens when I take a bucket of decanoic acid and throw it into water. It spontaneously forms these balls that you can't see easily. And on the outside is all the water-loving stuff, and on the inside is all the water-hating stuff. And so when we throw this into water, and this comes into contact with your dirty clothes, right? All the oil and grease will end up inside the ball. And that's how it makes water wetter. So it puts the grease on the inside, and then it can be carried off your clothes into the water. What other biological use do things like this have? That's true. That's a little more advanced than I want to get into. But you're not wrong. Think about everybody's born with these. What is it? What makes up our cells? What are we made of?
Cells.
We're made of cells. And cells are individual little, for lack of a better term, balls, right? Well, you know, a cell, when you go into biology, they always draw it like this, and they say, here's the nucleus, right, and here's the outside. They kind of tell you that. But really, that's not what a cell is. There's a cell membrane, right? And a cell membrane is actually a bilayer. Because remember, on the inside of the cell is water, and on the outside of the cell is water. And so we actually make our cell membranes like this, where you have head groups on both sides, and then the tails in the middle. And so in between in this so-called lipid bilayer is just grease, right? And this happens all the way around. And so that's how you can keep two separate areas of water from one another, is by forming this so-called bilayer structure, okay? You're going to be talking about that in biochemistry. Is your cells depend on these fatty acids to make cell membranes. You've got to have so much fat in your diet. You know, if you go on a really low-fat diet, it's hard to live. Your body needs these things, right? And yes, there are good fats and there are bad fats and don't eat too much and all that kind of stuff. And I'm not going to get into that. Those of you who are in nutrition know that better than I do, right? Clearly know it better than I do. But this is how we can use the properties of these fatty acids to our benefit. We can use them to clean our clothes, and we can use them to make cell membranes. Okay? And we do both quite well. That's the big use of these carboxylic acids. Okay? As we said, carboxylic acids are weak acids. Okay? The pKa values for most of these, again, are going to be between 4 and 7. This is the pKa for acetic acid, the principal acidic component of vinegar, right? It has a pK of about 4.76. You just determine the Ka, right, which is products over reactants. So the products is H3O plus, acetate negatively charged over the carboxylic acid, okay? And you figure out what the concentrations of all these things are. You can figure out what the Ka is. You then take that number and you take the negative log of it, and that gives you the pKa. And so remember that the smaller the number for pKa, the stronger the acid, right? 4.76 is small compared to 50. Remember, an alkane has a pKa of around 50. Carboxylic acid has a pKa of around 4.76, 4 to 5, just to call it, right? So, quite acidic in the grand scheme of things. Okay? We can also play around with that acidity. So here's the pKa. There's acetic acid, there's chloroacetic acid, there's dichloroacetic acid, there's trichloroacetic acid. Why is the acid strength increasing as I go from left to right?
Function activity.
Yeah. I've got electronegative groups close to that negative charge, right? Anything that can stabilize that negative charge is going to make it more stable. right? And if it's more stable, it's gonna form more of it, right? And so, yeah, so as we change out hydrogens for chlorines, the acidity goes up. What do you think would happen if we changed out the hydrogens for fluorine? Would it become more acidic or less acidic compared to the chlorine? Much more. Remember, fluorine's more electronegative than chlorine, right? And in fact, trifluoroacetic acid is a strong acid in what you learned in Gen Chem. It will completely dissociate in water, okay? And so that's why I was saying most of them don't completely dissociate, but you can make them that way. Trifluoroacetic acid is one that does, okay? Now let's skip that. Again, they react with bases, so this is how your soy sauce preservative is made. They take benzoic acid, which is only slightly soluble in water. Again, it's got 6 carbons and 1 carboxylic acid that doesn't satisfy our 5 carbon rule, but they will react that with sodium hydroxide and make sodium benzoate, and that is quite soluble in water. You can get up to 60 grams per 100 milliliters in solution. So that's very, very soluble, and it's a nice food preservative. Keeps the food from spoiling. Okay, you can do that quite easily. Okay, let's skip that. And then the last thing we'll talk about today is you can actually use this to your advantage to separate carboxylic acids from other compounds. We already talked about this in terms of how we can separate amines. Remember when we talked about the separatory funnel? But you can do that here for carboxylic acids as well. So here we've got a carboxylic acid that has a pKa of around, let's just call it 4.5. And you've got an alcohol here that has a pKa of around 16. That's a very different pKa difference. Both of these are going to be soluble in an organic solvent like diethyl ether. And then all I've got to do is add in some sodium hydroxide solution, shake it up, let the water separate from the diethyl ether. The sodium hydroxide will react with the carboxylic acid and make the salt, pulling that into the water. The sodium hydroxide isn't strong enough to deprotonate that, so it stays as the alcohol, and it stays in the ether layer. And now I can separate the two very easily. I just separate the water from the ether, right? And then I take that water layer and I just reacidify it with a strong acid like hydrochloric acid, and the benzoic acid will precipitate out as a solid, and I'll filter it off, and I've got my pure compounds. So you can use the acid-base properties to do this type of stuff very, very easily. Okay? All right, so for today, quiz 12, turn in 1219, please. Keep an eye out on your Canvas announcements. I will announce when we're doing review session. One will certainly be Sunday afternoon, so keep an eye out for that. I don't have as much flexibility in this one, and then I'll try to do something on Monday evening. So on your way out, just put your 1219 over there, and I will see you all later.